Now let us discuss this problem, quite interesting problem we have. So let us say we have a hemisphere, and this hemisphere is kept on a floor, and this is a smooth floor. So this floor is a smooth, mu is equals to 0, you can say. So for this floor, mu is equals to 0, and the mass of this hemisphere is capital M. Now there is a small mass m that is moving towards this hemisphere, and it collides with this hemisphere at angle of theta. So this collides at a point, that point makes a angle with the radius vector and perpendicular, that angle is given to you theta. So it collides with this hemisphere. Now what do you think? What can happen? So let us say, let me show you the collision. At the time of collision, what is happening? You see, at the time of collision you will have this kind of diagram. Okay, let us write first and then we will discuss next. So let us write those who have not written the first one. So let us write the first one. So let us see the second, at the time of collision. So what you will have at the time of collision? Now this is the situation at the time of collision. Are you getting? Now at this point of time, what you will have? So let me show you this one. Oh, sorry. So let us see at the time of collision and after time of collision. We have made the two diagram. So you see what we will have at the time of collision. We will have this is colliding. Now this has just before the collision, this is a velocity v0, and I can break this velocity in two-sided. So I can break this in the radial direction. I am also breaking in the tangential direction. So why I am doing this, you will understand soon. So now if this angle is theta, so this angle is 90 minus theta, because this angle is 90, so this angle is 90 minus theta. So this side component will be v cos 90 minus theta, so this is v0 sin theta. So velocity has a component v0 sin theta in this direction, and velocity has a component in this direction v0 cos theta. So just before the collision, this mass has a velocity in this direction and this direction. Basically I have broken this velocity, the x velocity, into two directions, radial as well as tangential. So this is my radial velocity v0 sin theta, and this is v0 cos theta, tangential direction. Just listen and then you write. Now after the collision, let us say this mass is rebounds back with a velocity v in the tangential radial direction. So in the radial direction, this is going with a velocity v. Now this is going in the tangential direction with a velocity v0 cos theta. That was earlier, before the collision. What was the velocity in the tangential direction? v0 cos theta. After the collision, what is the velocity in the tangential direction? v0 cos theta. Now I have a question. Why I have assumed that velocity in tangential direction remains same, but the velocity in the normal direction has changed? In the normal direction, velocity is v0 sin theta. Now this velocity is v. Coefficient of restitution is given to you. So you can write an equation in the radial direction using the coefficient of restitution. Let me first give me the answer why I have assumed that in the tangential direction velocity remains constant. There is a velocity v0 cos theta, v0 cos theta. Why this velocity remains constant in the tangential direction? Those who have not copied, please copy, and those who want to think, give me the answer. Okay, have you thought something? Now see, I have said these spheres are smooth. Generally it is assumed and it is given in the problem also. So sphere are smooth, this mass is also smooth. If this is the case, this sphere cannot apply a force in this tangential direction. You will have a tangential direction force only if there is a friction coefficient, because in the tangential direction you will have a friction force if there is a friction coefficient. But if I say this sphere is smooth, this mass is smooth, so there is no force in the tangential direction. If there is no force in the tangential direction, there will be no change in the velocity in the tangential direction, because to change the velocity I need force, but there is no force, and that's why in the tangential direction velocity remains constant, that is v naught cos theta. Are you getting? Now let us write, we can find how can we solve this. So I have two unknown, b and u. How can we solve? What kind of equation I can use? I can write one equation for coefficient of restitution, that is E, that is given to you. In the perpendicular direction, velocity of approach into E is equals to velocity of separation. So what is the velocity of separation? This block, so let me see, we can write one by one. So you see here, so we'll go slow. So now velocity in tangential direction will not change. We have already said this one. Now let us see, write the equation for coefficient of restitution. Now what is the initial velocity of approach? This mass is coming in this, so I have to write the equation in the perpendicular direction or in the radial direction. In the radial direction, what is the approach? This is coming with v naught sine theta. So the approach is v naught sine theta. So I have to apply E times velocity of approach. What is the velocity of separation? This mass is going with v this side, but this hemisphere has a u velocity this side. So what is the component of u this side? You will have u sine theta. You see, if you have v naught, then component in this direction is v naught sine theta. If you have a u in this direction, component will be u sine theta. I have already shown this here also. So you see, if this is v, that is the mass is going rounds back. Now u is in this direction. So if this angle is 90 minus theta, you can prove this one. So if this angle is 90, so this is a hemisphere velocity. So hemisphere will have a velocity in this direction u sine theta. So what is the separation? V plus u sine theta. You get it, because both are going apart to each other. So separation is v plus u sine theta. So I can write E times v naught sine theta is equals to v plus u sine theta. That is the equation of coefficient of restitution. So I have the equation 1. Now I can write another equation using the momentum conservation. So please write the momentum conservation equation yourself. And let me see how many of you are able to write. And those who have not written, let us copy. So you have to write down the momentum conservation equation in the x direction. If you draw the momentum conservation in the x direction, you will get a beautiful equation and you can solve these two equations. So writing the momentum for this mass is slightly a difficult one. You have to take the all component in x direction. For bigger sphere, okay, this is going in this direction with a speed u. So momentum of the sphere, hemisphere is, bigger hemisphere is m into u. But for a small mass m, you have to take the velocity component in x direction. All velocity should be written in the x direction. Basically this is the velocity in one direction v, another direction v naught cos theta. You have to take component. Okay, let me write the second equation. So what is the initial momentum in x direction? So initially this mass is going with v naught velocity, mass is m, so initial momentum in the x direction. This is in the rest, so this has only initial momentum mv naught. So initial momentum will be mv naught. Now finally this mass is going in this direction at speed of u, so it will have capital M into u. So for bigger mass we will have m into u, that is the momentum. Now for the smaller mass, let us say a smaller mass, this mass is going in this direction with speed v, and in this direction it b naught cos theta. What is the total velocity in x direction? I need velocity in x direction. So I will have mass into velocity in x direction. So let us say this velocity in the x direction is v naught cos theta, again cos theta, so v naught cos square theta, and this is a positive x, so v naught cos square theta. Now this velocity v is making angle theta with the vertical, so v naught sin theta, v naught cos theta in the vertical direction, v naught cos theta in the horizontal direction, v naught sin theta in the horizontal direction, and this is with negative sign because this is going this side, this is going this side, the previous one is going this side, and that's why it's positive. This is going this side, so this is negative, so I have to apply minus b sin theta. You have to show this theta yourself, you make a diagram yourself and you prove that the theta which I have written is correct. That is, you have to basically find what is the component of this direction, what is the component of this velocity in this direction. You are able to find this one or not? Let me see how many of you are able to do this one. So you have to find the x component of these two velocity, velocity v, that is the radially, and the velocity v naught cos theta, that is tangentially. So you have two velocities, a radial velocity and a tangential velocity. You have to break these two velocities in the x direction, that is you have to find the x component. Now next part is nothing, just solving the equation. I have two equations, 1 and 2. I can solve for u and b. So let us solve for u. So what we will do is, from this equation I can find the value of v and plug in this equation. So equation 2 I can write mb naught is equals to mu plus mb naught cos square theta. Now v sin theta, I can find v value from here. So v is ev naught sin theta minus u sin theta. ev naught sin theta minus u sin theta is v. So let us plug this value of v, ev naught sin theta minus u sin theta, and v into sin theta, so I have to multiply by sin theta also. So if you write something like this and you take the components mb naught, you take the u term one side, so you will have m, and from here you will have u, so this will be u sin square theta and into m, so u into m sin square theta. Now next term you will have mv naught cos square theta, this term, and here we will have one term, ev naught sin square theta into m. Are you getting? Now if you take common everything, you will get the final result something like this. You solve yourself, you will get this result. So this is the u velocity, velocity of rebound back. So this is the velocity of hemisphere. So this is the velocity of hemisphere. So what we have learned in this problem, so you see in this problem 2-3 points is important. First point is, in the tangential direction, if the spheres are smooth, the collision is smooth, in the tangential direction there is no change in the velocity. This is the important point. So you will see there are many kind of problem you will find in which tangential direction, if you use, velocity remains constant, the problem becomes easy. Now the second part is, the velocity of approach times e is equals to velocity of separation is true only in the perpendicular direction. So this is the direction of collision. So if it is colliding, so this equation can I write only in the direction of collision, that is the direction of perpendicular. Are you getting or not? So the two surfaces are contacting to each other. So in the direction of normal reaction, this equation is valid. Now you see, in this equation we have to also write the third important point we learned in this question is, momentum conservation. So you see the velocity for a smaller mass, we have a two velocity, radial component and tangential component. I have to break these two components in the x direction, and then I can write total momentum of a smaller mass m in the x direction. That I have to do, that is that I have to take the component, and then nothing else, then just we have to solve the equation. So I think all of you have written this one. Okay, so if you have copied this one, let us discuss the next problem.